So let's begin. So in the last class, we were discussing about four wave vectors and also uh, something about four momentum. And as I told you, four momentum and four wave vector, they are a related quantity. You can, if you are dealing with a photon or even particle, you can connect them. So here we are specifically talking about photons or electromagnetic waves, and we discussed about the Doppler effect and the transverse Doppler effect based on the Lorentz transformation of four wave vectors. So today let us solve a couple of problems. So I will just show you a couple of examples, then you can solve analogous problem yourself. So I will just today discuss a couple of problems. So let me just give you a one problem first. So we have already discussed about the formula. This is straightforward problem. So suppose you have a two inertial frame. Okay, one is at rest, another is moving with velocity v along the x-axis. So now you have to remember, as I told you, that you have to choose your formula based on where the source is, right? The source could be in the moving frame or source could be in the rest frame. So that will depend on the problem. You have to read the problem carefully and then decide which transformation to apply. So in this particular example which I am talking about here, consider an inertial frame S where a monochromatic electromagnetic wave, say with frequency nu, propagates in a particular direction which makes an angle say 60 degree with the x-axis. And the source frame S, so S prime and S, there are two frames. So the source is in the S frame, right, which is which is moving with velocity v, and the photon which is emitted in this frame is propagating along a direction which is a 60 degree, which is making an angle 60 degree with the x-axis. And suppose the velocity v is given to be 4/5c, right? And there is an observer which is situated in another inertial frame, say S prime. And let us imagine that the axes are parallel in these two frames, that is x, y, and z axis in these two frames are parallel with each other. And you have to determine the frequency and the angle in the another frame, say S prime frame. So let me just draw the pictures. Uh, Suppose this is one frame. This is, say this we are calling the frame S. And in this frame, a photon is, or electromagnetic wave is propagating in this direction. Say the angle is say this is x-axis, say this is y-axis, and this is z-axis, and this angle is 60 degree is given to you. And we have another inertial frame here which we call S prime. And now don't I mean assume all the time that S prime frame has to move. I mean, it's up to you. You're just labeling the frames as S and S prime. So usually we label S prime as the moving frame and S is the frame at rest, but it's not necessary. It's up to you. How do you label them? And then you have to write down the transformation. So for example, in this frame, this is origin O, this is O prime, this is X prime, Y prime, and Z prime, and the observer is in this frame, right? And the source is here in this frame, and this source is now moving. Earlier in the previous example that I discussed in the previous class, the possibly you may remember that the observer was moving and the source was at rest. In this particular example, the source is moving, right? And it could be in any particular direction. I'm again taking a particular direction, that is the x direction, but from problem to problem this may change. So you have to be careful about which formula to use and how to write down the appropriate transformation. So this is a pretty straightforward problem. So observer here, and the observer is measuring the frequency and angle, right? Then this is the S frame where the photon is emitted at angle 60 degree, and say the frequency is nu. Frequency is nu, right? And you have to determine what is nu prime in this frame. So in this frame, if I want to calculate nu prime, the formula is straightforward. Only thing is that you have to remember about the sign that you have to use, because it depends on the transformation, where the source is and where the observer is. So in this case, I possibly talked about this, that gamma into 1 plus beta. Sometime it may become 1 minus 1 minus beta cos theta. In this case, 1 plus beta cos theta. This comes from the Lorentz transformation of the 4-wave vector, which we have already discussed. This is gamma factor. Again, gamma, you should always remember, and that gamma is always associated with a particular velocity. In this case, there is only one velocity v, which is associated with the velocity of the frame. So gamma is basically gamma v, beta is v by c, and it is already given to you that that beta is v is given equal to v, the mod of v, basically velocity is given to be 4 by 5 c. This is given. So 4 by 5 c is the velocity, angle is 60 degree. So what's the frequency here? Straightforward, you plug in this formula. So this is simply 1 plus beta cos theta, which is basically beta cos 60 degree. Beta is also known to you, so just you can write down, okay, let me write down one line here, and gamma is square root of 1 minus beta square, right? So you just put these values, beta equal to how much, 4 by 5 c, which will be how much, I mean beta is v by c, so c gets cancelled, it will be 0.8, and you have cos 60 degree here, cos 60 degree. So put the values, 1 plus 0.8 cos 60 degree divided by 1 minus 0.8 square times nu. So if you calculate this number, you will find this will be 7 by 3 nu, and we can see that the frequency is increasing, right? Clearly, since the source is moving towards the observer, the frequency of the electromagnetic wave will be higher, right? This is called blue shift. It's not red shift, right? Frequency is increasing. 7 by 3 is a number which is greater than 1, of course. It will be something 2 point something. So the frequency is more than double as compared to the frequency in the rest frame of the electromagnetic wave. And if I ask you to calculate the angle of observation, that you can also calculate what is the angle of observation in this frame. On that frame, it is 60 degree. So in this frame, angle of observation in this frame, let us call this S prime frame, and this is S frame. And I again and again tell you that don't get confused with this prime and unprime, right? It is up to you. Depending on a problem in a given situation, you may start with, I mean, you see this derivation of this formula is not going to be difficult. It's straightforward, right? You know the 4-wave vector omega by c. It depends on I mean the time component is omega by c, and then you depending on which direction the photon is traveling, you can write down the spatial component of the 4-wave vector, and then apply appropriate transformation. Even if you don't remember this formula, nothing to worry. Right, you can find out by applying a Lorentz transformation, but it is always useful to remember this, because then it will not take much time to solve the problem. Okay, angle of observation, we have talked about this. So cos theta, in this case cos theta prime will be cos theta. Earlier it was minus beta, so it will become plus beta. Velocity is different here, 1 plus beta cos theta. And you can put the values. Cos theta, as we already talked about, cos 60 degree is 0.5, half. Beta is 0.8, and you can write down 1 plus 0.8 times 0.5. So if you put the values, it will come out to be around 13 by 14. So theta will be cos inverse of this. So if you use a calculator, you can find out theta prime will be 21.8 degree. You can clearly see the angle is far different than this, right? 60 in this frame it is 60 degree. In this frame it is 21.8 degree, and this is called aberration of light, as you have already discussed in previous class. So the frequency and the angle of observation both is going to change from one inertial frame to other, right? So this is a these are the two physical phenomena. One is called Doppler effect, and this is called aberration, right? Of course, you should remember, I also talked about transverse Doppler effect, but this is not a transverse one, right? This is the usual Doppler effect. Only thing that I have changed is the observer and the source frame has been switched. So you can put your observer wherever you like. In this particular case, since the frame is source is moving, that's why I have to consider this frame as the moving frame, and the observer is rest and the S prime frame. Of course, you could have labeled this to be S and this to be S prime. Then you have to write down the transformation appropriately. That it is up to you. See, nobody is going to take that responsibility. Don't use the formulas blindly. You have to analyze the situation and based on the given inputs. So what are the things that is given to you, and how to use the appropriate formula. That is the only caution that I mean issue all the time when you are using this kind of formula in relativity. Okay, so this is one problem. You can actually construct many such problems. So this is a quite trivial problem. Uh, Let me just discuss another problem here. Um, okay, so now let us imagine another situation where, say, there is a mirror which is moving through vacuum at, say, speed v in the x direction, and an electromagnetic wave with frequency, say, omega I or nu I, if you consider the normal frequency, it is normally incident on the mirror from, say, x equal to plus infinity. And if someone asks you, calculate the frequency of the reflected light, so mirror is moving along the x direction. So let us first draw that picture. So we have, say, a y axis here, and, say, x axis and x axis here. This is the x axis, and so there is a mirror here, right? So somewhere here, that mirror, right? This mirror is moving, right? So moving along, say, x direction with velocity v. So what is the given problem? So some electromagnetic wave is propagating in the x direction. It is approaching the mirror from the, say, plus infinity. So again, you can attach a frame to the mirror itself, so which you can call this is y prime, and of course, since they are parallel, you can also call this x prime, right? X prime, x and x prime are the same. Same means, I mean, they are collinear, parallel, and this mirror is moving. And imagine an electromagnetic wave is coming from this direction, right, which has a frequency, say, omega I, omega incident in this frame, right? Now, someone in the lab frame, so there is two frame. One is the lab frame, another is the mirror frame. Mirror is moving with velocity v, right? And we have to figure out what is the reflected frequency of the reflected light. So you may wonder, that is, we have already learned about the laws of reflection, right? The angle of incidence and the angle of reflection, they usually become same in a given frame. So but here there is no angle of incidence, it is 90 degrees, so it's a normal incidence. So you don't need to worry about the laws of reflection here. So you just need to apply the transformation of four vectors, right? So we have already learned how to write down the different components of a four-wave vector. So in this particular case, so there are two frames. One frame you may assume to be lab frame, which is at rest, and the mirror frame, which is, let us call that S prime frame. But again, remember, I mean, it's S and S prime. Don't get into that prime and prime. This may sometimes confusing. I repeatedly tell you that this is because I will write down the transformation here, because if I want to calculate the four-wave vector in the mirror frame from the lab frame, so then I have to apply the appropriate transformers. For example, let us call the quantities in the mirror frame to be primed quantities, right? And in the lab frame to be unprimed quantities. So in that case, so let us first write down what are the wave vector component of the wave vectors. Let us call the prime quantities to be in the mirror frame, omega I prime by c. This is the time component. Then let us write down the spatial component. Let us, for the time being, write just then kx prime, ky prime, kz prime. The omega by c, kx, ky, kz are the four components of the four-wave vector. And this is just very simple transformation, because the frame is moving along the x-axis, and we want to calculate the prime quantities in the moving frame. So we just have to apply this transforms, gamma minus beta gamma 0 0, and this is the usual transformation along the x direction, is 0 0 0 0 1 0 and 0 0 0 1. So and what are the components in the unprimed frame, that is the lab frame. So someone is observing the light in the lab frame, right? So this light is observed in the lab frame. So this is omega I by c. This light is coming from this direction and getting reflected by a moving mirror, right? That is the problem. It's reflected by a moving mirror. So this is time component. What is the x component? What is the x component of the four-wave vector in the lab frame? What is kx? Like here I have written kx prime, ky prime, kz prime, right? What is ky prime? What is kz prime? Tell me these three quantities, right? Kx prime, ky prime, kz prime. What is kx prime? For this wave is coming from this direction and moving towards minus x direction. So what is the kx component of the wave vector, for wave vector? Can you hear me? Hello.
Yes, sir. Yes, sir.
Sir,
Okay.
omega I by c cos theta
Why cos theta? There is no angle of incidence here. This is 90 degree, right? So it's not a oblique incidence.
zero.
So cos theta and sin theta will appear only when you have an oblique incidence, right? So then you have to take an appropriate component. In this case, you see the wave is coming parallel to the x-axis, right, from infinity. So just think clearly, right? That is my suggestion, that you have a photon or electromagnetic wave which is propagating along the x direction. So if some electromagnetic wave is propagating along, so to talk about the three wave vector, forget about four wave vector. Just tell me what is the direction of the wave vector. If a wave is moving along the x axis, what is the x component of the three wave vector?
Sir, omega I by c হবে.
Okay, omega I by c, that we have already learned, right? It is omega I by c, and then depending on direction you may break into components. But here there are this particular wave is traveling along x axis only, no y component, no z component. So you can straight away write ky equal to 0, kz equal to 0. You don't need to think at all, because it is moving along only x direction, right? And which x direction? Negative x direction. It is moving in the negative x direction. So there is a direction, right? Positive x or minus negative x? Negative x. So I write here minus omega I by c, right? This will be the x component of the four wave vector will be minus omega I by c, because it is moving in the minus x direction, right? Because see, the last three components of the four wave vector are nothing but the three wave vector. That you should remember. We artificially separate them. We think that frequency is different thing and wave vector is a different thing. That is an artificial construction that we are familiar with. But in relativity, in four dimensions, there is no such thing. Frequency and wave vector are the same thing. They are just different component, time component and spatial component. So only thing that you need to think about is what is the three wave vector. The three wave vector is minus omega I by c. Y component is 0, because it is only traveling along x direction. Z component is 0, right? If you multiply and simplify this, you get omega I prime. I'm not multiplying all the four quantities, because right now I am only interested about frequency. So the first component will be sufficient. Let us write down what is omega I prime, because c is on the both sides, so that will get cancelled. I'm not writing that, because that's automatically cancelled. Omega I prime will be omega I, right? And gamma is the first gamma, and then we will have 1 plus beta. Minus minus becomes minus, and this minus becomes plus. So gamma into 1 plus beta, right? This is the frequency in the moving thing. You can also write, if you this is angular frequencies, if you want to write nu in terms of nu I prime will be nu I into gamma into 1 plus beta. Now you should remember what are the, see, don't just apply Lorentz transformation blindly. As I repeatedly telling you, you should always think what you are calculating, where you are calculating. See, this nu I prime is the frequency of the incoming light in the mirror frame. Okay, but what is the problem about? The problem is asking you to calculate the frequency of the reflected light in the lab frame. It is not asking you to calculate the frequency in the mirror frame. What we have calculated right now is the frequency of the incoming light in the mirror frame. So in order to get this frequency in the lab frame, we have to again apply another transformation, because this quantity is in the mirror frame. We have to calculate the quantity, the associated quantity in the lab frame. So how do I do that? Because again, it's another transformation. So and tell me what is the frequency of the reflected light in the mirror frame. If you know the frequency of the incident light in the mirror frame, you can easily tell me the frequency of the reflected light in the mirror frame, because in the mirror frame the incident light and the reflected light must have the same frequency, right? Because the mirror is at rest in its own frame, the mirror is not moving. So whatever light is being reflected by the mirror must have the same frequency as the incoming one, right? So incoming electromagnetic wave and the outgoing electromagnetic wave in the mirror frame itself must have the same frequency. That means the you already know that omega r prime must be equal to omega I prime in the mirror frame. So it is only in the mirror frame, of course not in the lab frame. So if you want to calculate this same quantity in the lab frame, I have to apply another transformation. So let us write down that. Say this one is for reflected light, The previous one was for incident light. So for the reflected light, what are the component? Omega r by c, and we already know that omega r is also, if we compare omega r and omega I, in see omega r is the something, because in the mirror frame incident and reflected are same, but what is being reflected by the mirror is again observed by the observer in the lab frame. But you have to remember that in this case, since the mirror is moving, that's why that difference will appear here, right? The mirror is moving, so there is a Doppler effect associated with this problem. So omega r by c, and then where is that? Omega r by c. Maybe you can go to the next page. Little space left. Page. Okay. So the next. So earlier in the previous case, we have already obtained that nu I prime, or omega I prime equal to omega I times 1 plus beta times gamma. This we have calculated, and we know that omega r prime equal to omega I prime, because the mirror is not moving in its own frame, but in the lab frame the mirror is moving. That you have to remember, right? That's why all the differences are popping up. So omega here, if I write omega r by c is the time component, and let us write down the for the reflected wave vector kx, ky, and kz are the spatial component of the 4 wave vector. Then you see you are making an inverse transformation. You know the quantity in the prime frame, that is the moving frame. You want to calculate the quantity in the lab frame, which is at rest. So in this case, your sign will change. So gamma, beta gamma, 0 0, beta gamma, gamma 0 0, 0 0 1 0, and 0 0 0 1. So this is the Lorentz transformation matrix, and the 4 components of the wave vector in the prime frame, that is mirror frame. Omega r prime by c. This time you see, this time the reflected wave. Earlier, what was the situation? If you remember, this was the lab frame, right? This is lab frame, and the mirror is this one, which was moving along this x-axis, right? X or x prime, and the photon was coming from this direction, right? Nu, right? So the omega I was, the omega was I by c was positive in the previous case, right? Because the wave was traveling in the minus x-axis. When the wave is reflected, remember this will travel along this direction, right? Incident wave is traveling along minus x-axis. The reflected wave will travel along the plus x-axis. So that's why for the reflected component, you should write omega r prime by c, not minus omega r prime by c. So that's the difference. You should remember that. And y and z component are of course 0, because there is no component along y and z direction. And then again, this is a straightforward application. The matrix multiplication, you just do that. So omega r, I am not repeating that. Omega r will be gamma times 1 plus beta omega r prime. And you already know what is omega r prime, right? From this, because omega r prime is omega I prime, and omega I prime is known to you. So you just put it here, gamma times, say I want to calculate nu r. So gamma times omega 1 plus beta, and nu r prime, and nu r prime is already known to you. So you just put it here, gamma times 1 plus beta, and nu r and nu I are same. So nu I prime, and since we have calculated this earlier, so there are 2 gamma factor, gamma square into 1 plus beta square times gamma I, right? So we are calculating the frequency of the reflected electromagnetic wave in the lab frame in terms of the frequency of the incident electromagnetic wave in the lab frame, and the velocity of the moving mirror, right? So if you simplify this further, because gamma square equal to 1 plus 1 by 1 minus beta square, so you can simplify it and write down 1 plus beta, not square root of 1 plus beta and 1 minus beta nu I, right? So this will be the frequency of the reflected light in the lab frame. Okay. So as you can see, these problems are, once you get familiar with, you can easily solve such problem. So I will discuss another problem which is not just a bit complicated, because you can also make the situation a bit complicated by making an angle, right now there was no obliqueness here in this problem, because the electromagnetic wave was incident normally, But suppose now in the same problem, if I make a slight change and demand that the wave is coming, say, along some particular direction, say 30 degree or 25 degree, or say some arbitrary angle theta I, right? Then you have to think clearly, because you see, then you have to apply the laws of reflection here, because theta I and theta R, say, are the angle of incidence and angle of reflection. We have learned about aberration, and we know that the angles are not going to be same in all inertial frame. But of course, if you are only considering about the mirror frame, in that frame the angle of incidence and the angle of reflection must be the same, because it is the law of reflection in that frame, because the mirror is at rest in that frame. So angle of incidence and angle of reflection in the mirror frame will be same, but not same in the lab frame. So let us discuss the problem. I first tell you the problem and then we'll solve it. Okay, so it is I mean another version of the same problem. So let me just draw the picture, then it will be clear. Then I will explain in words. So suppose let us choose our reference frame. So suppose this is okay, y, and say this is say x, this is y, right? And say this is a mirror. Okay, I'm drawing the quantities in the, say, lab frame. So someone in the lab is observing the mirror, and he finds that the electromagnetic wave comes from a particular direction, say theta I, with an angle theta I. Let us call this frequency to be nu, or nu I if you like, and the wave vector is a ki, because now it has a component. It is not simply omega, as someone was telling, that it will be something cos theta, maybe sin theta, depending on which component you are talking about. Ki and the reflection along, say, this direction, let us call that as kr, wave vector. This frequency, and so this angle is theta r, right? Now tell me, this frequency and the repeated frequency, will they be same? In the previous case, we have already discussed such a problem, right? The angle will be same in the mirror frame. If I look in the mirror frame, some light is coming, it's incident and reflected, right? And let us call this a nu prime, right? And we know only nu, we have to calculate all the prime quantities. But in the mirror frame, if you see, this is okay, I should tell you that, because otherwise things could be confusing. Okay, okay, so maybe I have drawn it in a bit confusing way. Okay, let us call this to be, so this mirror is moving with velocity v. Okay, so someone is observing in the lab frame. So this x-axis and y-axis basically are the axis of the lab observer, right? So otherwise, okay, maybe should I redraw it? Okay, no problem. Let me just tell you that there is an x-axis and y-axis. These x and y-axis are not in the mirror frame. This is lab frame. I'm just writing that lab frame. So someone is observing the mirror in the lab frame, right? Lab frame. So x-axis and y-axis are the axis of the observer in the lab frame, and that observer is observing all these quantities, nu, theta I, theta r, ki, kr, nu prime, in the lab frame. And as I told you, that incoming frequency and the reflected frequency are not necessarily the same in the lab frame. They are going to be different, right? And but of course, in the mirror frame, as you have talked about, in this case also, since you are observing in the lab frame and the mirror is moving, the angle could be different. And let me just draw the same picture in the mirror frame. Okay, so mirror frame is moving, so that's why I'm here using a prime notation here. They say this is y prime. This is a mirror frame. In the mirror frame, if someone is attached to the mirror which is moving, so this is a mirror frame. Okay, this is a mirror frame. Mirror frame. In this frame, the axes are x prime and y prime. There is no motion along the z direction, so I'm just not writing any z axis here. So in this case also, and the phenomena is same. Some light is coming from some direction, getting reflected in another direction. So let us just label the quantity by using a prime quantity, ki prime. Let us call this to be kr prime, and this angle to be theta I prime. This is to be theta r prime, right? So your job is to calculate these primed quantities in terms of the unprimed quantities or reflected, say, you may call it a sometimes this new and new prime could be confusing. You may also use it with new I incident and then the new R reflected, right? New I is for incident and new R is for reflected. Okay, so let us use that. New and new prime may not be very good thing to write. New I, okay, may not be, because prime, I'm using prime here and you may get confused why I'm writing prime here, right? That can be mixed up, right? So I think I should write new I and new R, right? A new, not new prime. So new I and new R are the incident and reflected waves frequency in the lab frame. Similarly, you will get new I prime and a new R prime in the mirror frame, right? And we want to calculate this angle of reflection theta r. Of course, see, theta I prime is going to be equal to theta r prime, right? And new I prime is going to be equal to new R prime. But that is not the case in the lab frame. We have already learned that the angle are going to be different because this wave is coming from different direction. This wave is going into some other different direction, right? Earlier in the previous example that I talked about, that was case of normal incidence. There was no angle associated with that. It's 90-degree, right? It's just normal incident, right? But in this case, we have a different angle, theta I and theta r. The angle of incidence and the angle of reflection are same in the mirror frame, but not in the lab frame. We have to calculate the angle of reflection in the lab frame in terms of the angle of incidence, theta I. What will be theta r in terms of theta I and say velocity v, right? Also, you have to calculate what is the reflected frequency. Suppose you know nu I. Somebody told you that nu I is equal to say 320 hertz, nu I. What will be nu r? You have to calculate that in the lab frame, not in the mirror frame, right? So that is the problem. This is the problem. Is the problem clear to everyone? If you have any doubt, okay. So the solution is quite similar. So so let us just move in the same fashion. It's not very difficult. Only thing is there cos theta and sin theta component that you have to carefully write. And so let us write down the four wave vectors. So in the mirror frame, let us write down the incident wave vector. So omega I prime, right? Mu I or omega I is in the lab frame, right? In the mirror frame. So omega I prime by C, and then we write the special component kx prime, ky prime, and kz prime. And so these are basically, you can also write down them explicitly by breaking them into components. So okay, let me write that. Possibly that will be easier to understand. Omega I prime by C. You can see what will be the kx prime in the prime frame. In the prime frame, you see this wave is going in this direction. So it will have two components. One is along this, one is along this. What is this direction? This is negative x direction. This is, sorry, this is positive y direction. So positive y component, negative x component, right? For this one, we have positive y component, negative x component. That's why I write here minus of omega I prime by C and cos, of course, theta I prime. Because it is in this frame, right? Cos theta I prime. And y component is positive. If this is your cos theta, that will be sin theta. Y component omega, that will be positive. That should remember. One is positive, one is negative, right? Omega I prime by C sin theta I prime. Z component is of course 0, right? These are the four components of the four wave vector. And then we have to apply the appropriate transformation, which is again same. Maybe I should write, or it is same gamma minus beta gamma, because minus beta gamma 1 and all are 0, right? So that's same. I'm not writing them again and again. And what are the components of the four wave vector in the lab frame? That we know, right? Omega I by C, because it is omega I, and again the x component will be negative, y component will be positive. Omega I by C cos theta I plus omega I by C sin theta I and 0, right? So let us write down the equations, simplify the different terms. So if you write down the time component, omega I prime by C equal to omega I by C gamma into 1 plus beta cos theta I simple. Just take this one, multiply this one with this, that one with that one. Okay, maybe 0 0 if I write, that will be easier. 0 0 0 0 0 1, right? So this is the first equation, from which if you like you can write down them in terms of nu also. C can be dropped from both sides, writing nu I prime equal to nu I times gamma into 1 plus beta cos theta I. This is nu I prime. The second equation that involves a negative sign, omega I prime by C cos of theta I prime equal to minus omega I by C, and then gamma, and then beta plus cos theta I, beta plus cos theta I. Again, you can write down in terms of nu. So nu I prime cos theta I prime, C is dropped, cos theta I prime equal to nu I into gamma, nu I into gamma into beta plus cos theta I, because this beta, this is the quantity in the right hand side, beta plus cos theta I. The third equation, that is simplest one, omega I prime by C sine of theta I prime will be equal to omega I by C sine theta I. And if you write in terms of nu, C is again dropped, nu I prime sine theta I prime will be equal to nu I times sine theta I. So we have three equations, these three relations, and we have to calculate the similar primes for the reflected wave. Remember this, the entire analysis that we have done in this page is for the incident wave, not for the reflected one. So the task is quite, straightforward. I mean, you just have to apply the similar transformation for the reflected wave vector. Only thing that you should be careful is the sign of different components, because the reflected wave is moving along some other direction. You see the reflected wave, if you see the reflected wave is moving along the plus direction, right? So both the components will be positive. In the first case, you see the x component was negative, y component was positive, whereas for the reflected one, both x component and y component will be positive, right? You can see here, right? This is the reflected wave, right? For the in the mirror frame. So this is the x component, this is the x component, and this is the y component. Both x component and y component will be positive in this case. So you should be careful about the sign.
হ্যালো স্যার
So let us বলো
বলছি ফার্স্ট কেসটা এক্স কম্পোনেন্টটা নেগেটিভ কি করে হচ্ছে, এক্সটা তো পজিটিভ।
আচ্ছা, কেন হবে? নিউ পে কোথায় গেল? পেজটা দাঁড়াও, দেখা যাচ্ছে। আচ্ছা, আমি আবার আঁকছি। ওকে, মেবি আই শুড ক্লারিফাই ইট again. Okay, let me just draw the picture in the let's say mirror frame. Okay, this is the mirror, this is the mirror. আমি মিরর ফ্রেমে আঁকছি এটা, ঠিক আছে? মিরর ফ্রেমে। So this is the incident wave, this is the reflected wave, this angle is theta I, this angle is theta r prime, sorry, all are mirror frame, and this is a kr prime, ki prime. এবার বলো কি করে পজিটিভ হচ্ছে? এটা যদি এই ডাইরেকশনে হয়, এই যদি কম্পোনেন্ট নিতে হয়, তাহলে কি করে পজিটিভ হবে বুঝলাম না। এটা যদি এইদিকে যায় তাহলে দুটো কম্পোনেন্ট থাকবে, তাই তো? এই অ্যাঙ্গেলটা থিটা হলে এটা অ্যাঙ্গেলটা থিটা হবে নাকি? এটা যদি থিটা হয়, এই অ্যাঙ্গেলটা থিটা হলে এই যে প্যারালালটা নিয়ে এটা থিটা হবে তো, থিটা আই প্রাইম।
আচ্ছা,
হবে তো, তাই তো? তাহলে এবার দেখো, তাহলে যদি এই কম্পোনেন্টটা আর এই কম্পোনেন্টটা নিই, তাহলে এটা কোন দিকে? এক্স কম্পোনেন্টটা কোন দিকে? এটা তো ভেক্টরটা, দিস ইজ দ্য ওয়েভ ভেক্টর, রাইট? থ্রি ওয়েভ ভেক্টর। তার যদি এক্স কম্পোনেন্টের এটা কোন দিকে? এটা যদি প্লাস এক্স ডাইরেকশন হয়, এটা কোন ডাইরেকশন? এটা কোন ডাইরেকশন? প্লাস অন মাইনাস? নেগেটিভ হবে। আর তেমনি ওয়াইটা হচ্ছে পজিটিভ, রাইট? এখানে ওয়াইটা পজিটিভ, এক্সটা নেগেটিভ। এখানে তুমি নাও, এখানে কি হবে? এখানে তুমি কম্পোনেন্ট নাও, right? Suppose this is the wave vector, right? This is your x component and this is your y component. তাহলে x টা কোন দিকে? প্লাসের দিকে। এটা যদি থিটা হয়, এটাও থিটা হবে, থিটা আর প্রাইম, তাই তো? তাহলে এটা যদি x কম্পোনেন্ট হয়, এটা যদি y কম্পোনেন্ট, বোথ আর পজিটিভ। ইনকামিং এর জন্য একটা নেগেটিভ হচ্ছে, একটা পজিটিভ হচ্ছে, এক্সটা নেগেটিভ, ওয়াইটা পজিটিভ। ক্লিয়ার?
হ্যাঁ স্যার।
If you have, okay. Okay, so let us now do the same exercise for the reflected wave. So omega, for the reflected wave, we are writing the 4 wave vector in the prime frame. So we have to write down the 4 components omega r prime by c, যেমন বললাম আমি যে দুটো কম্পোনেন্টই পজিটিভ হবে, x y component omega r prime by c cos of theta r prime, right? Omega r prime by c sin of theta r prime, and then you have 0, right? এটা হচ্ছে তোমার 4 wave vector of the reflected 4 wave vector, right? For components, and you see you have the same kind of transformation. এখানে আমরা কিছু ইনভার্স ট্রান্সফরমেশন করছি না, যেভাবে করেছি ল্যাব ফ্রেম থেকে মিরর ফ্রেমে যাচ্ছি, মিরর ফ্রেমটা মুভ করছে, তাই আমাদের এটা হওয়া উচিত গামা এক্স ডাইরেকশনে মুভ করছে, বিটা গামা 0 0 মাইনাস বিটা গামা গামা 0 0 0 0 1 0 0 0 0 1, and similarly write down the components here. Omega r by c, omega r by c cos of theta r, এরকম পজিটিভ হবে, যেই ফ্রেমে যাও না কেন এটা পজিটিভ হবে। Omega r by c sin of theta r, and 0. Again we just do this just matrix multiplication and equate the components. So omega r prime by c will be omega r by c times gamma, এখানে মাইনাস হবে, এই মাইনাসটা আর প্লাসটা মাইনাস থাকবে, ওখানে মাইনাস মাইনাস প্লাস হয়ে যাচ্ছিল, তাহলে 1 মাইনাস বিটা কস অফ থিটা আর। যদি নিউ টার্মসে লিখি তাহলে লিখবো নিউ আর প্রাইম ইজ ইকুয়াল টু নিউ আর টাইমস গামা ইন্টু 1 মাইনাস বিটা কস অফ থিটা আর আর। Similarly from the second equation, you just write omega r prime by c cos of theta r prime is equal to omega r by c gamma times cos theta r minus beta, এই মাইনাস আছে এখানে, মাইনাস বিটা গামা কমন নেওয়া হয়েছে, দেখো এখান থেকে বেরিয়ে যাবে নিউ আর প্রাইম সি বেরিয়ে যাবে cos theta r prime equal to new r gamma times cos theta r minus beta. Similarly, the third equation becomes omega r prime by c sin theta r prime equal to omega r by c sin theta r, right? That is written in terms of new r prime sin theta r prime equal to new r sin theta r. তাহলে এখানে তিনটে ইকুয়েশন, আগেরটার জন্য তিনটে ইকুয়েশন, we have total in total 6 equations, right? Again, it is difficult to remember all of them. If you write them clearly, you can assemble them, simplify them. So just I'm writing the equation here. So then you see don't forget what was the question. Question was the incident frequency is given in the lab frame. You are asked to calculate the frequency of the reflected light. Just the same problem which was discussed in the previous case of normal incidence. In this case, only difference is there is an angle of incidence, and that makes all the things a bit more more detail oriented. So in this case, the principle is same. In the mirror frame, if someone asks you what is the angle of incidence, relationship between angle of incidence and angle of reflection, they must be same. In the mirror frame, the mirror is not moving. If someone is attached to the mirror, for that person, if suppose you are enclosed in a closed box, inside a closed box, there is a mirror, right? Some light is getting reflected by the mirror. In the mirror frame, unless you look outside, you will never know that you are moving, right? If you are moving with uniform velocity, you are not moving, right? The outside is moving. If you even if you look outside, it may appear the outside is moving. So in that frame, the incident frequency and reflected frequency also has to be same. And the angle should be also same. So new reflected prime must be equal to new incident prime, and the angle of incidence and the angle of reflection, rather I should write theta r equal to theta I prime, theta r prime equal to theta I prime. Angle and frequency are same in the mirror frame. Remember, I am talking about the mirror frame, not in the lab frame. If I go to the lab frame, they are different. They bound to be different, because in that frame, the mirror is moving, the angles are different because of the aberration. So based on these 6 equations that we have obtained, we can simplify this equation and find out a relationship between the reflected frequency and the incident frequency, the reflected and the incidence angle and the reflected angle. Let us do that. Okay, so I am just taking ratio. So 1, 2, 3. There are 3 equations for the previous case. For the second case, we have 3 equations. So altogether 6 equations. So I'm just taking the equation ratio of the first equation with the fourth equation, second equation with the fifth equation. And the third equation with the sixth equation. So I'm writing nu r prime divided by nu I prime. Now you know this has to be same, right? This you already know that this has to be equal to 1. And you have got some expression for nu r prime and nu r prime, nu I prime, right? So because from the this matrix multiplication that we have done in the previous page, so I'm just writing them: nu r gamma 1 minus beta cos theta r divided by, okay, nu I gamma 1 plus beta cos theta I. Note here it is theta I, it is theta r, right? Of course they will be different because we have done the transformation for the incident 4-wave vector and the reflected 4-wave vector. And the incident 4-wave vector, the components are different. For the reflected 4-wave vector, the components are different. For the incident wave, frequency was nu I prime. For the reflected one, it was nu r prime. And in the mirror frame, they are equal. They are bound to be 1, right? So this can tell you that these two are equal because this equal to 1. So you can also write nu r by nu I. Gamma will get cancelled. You can straight away write nu r by nu I equal to 1 plus beta cos theta I divided by 1 minus beta cos theta r, right? Let me see how much time. Okay, still 10 minutes. Okay, and then if I take the ratio of the second equation with the fifth equation, then I get nu r prime by nu I prime equal to nu r cos theta r minus beta divided by nu I into beta plus cos theta I. Again, you know this has to be equal to 1. This has to be equal to 1 because the frequency are same in the mirror frame, right? So that tells you that nu r by nu I is equal to beta plus cos theta I. This will go on the numerator, cos theta I divided by cos theta r minus beta. And the last one for the third ratio of third and sixth, nu r prime divided by nu I prime, you get nu r sine of theta r divided by nu I sine of theta I. Again, they are same in the mirror frame. That's why I'm writing them to be equal to 1. And this is telling you that nu r by nu I should be equal to sine theta I by sine theta r, right? But remember, we have to finally calculate nu r in terms of nu I and the velocity, not in terms of theta I and theta r, right? Because inputs are theta I and nu I, not theta. See here, although we are getting nu r in terms of nu I, but since there are theta I and theta r, we have to simplify it further. And that's not difficult because all that you need to do is basically equate, because these are the same quantity, right? Nu r by nu r prime by nu I prime. We have calculated them repeatedly. Nu r by so this one, if you look at this equation and this equation and this equation, all are the ratio of nu r by nu I. So if we equate this one with this one, right, what do I get? I write 1 plus beta cos theta I divided by 1 minus beta cos theta r should be equal to beta cos theta I divided by cos of theta r. Maybe I should go to the next page, otherwise it will be difficult to understand. So let me write down it: 1 plus beta cos of theta I divided by 1 minus beta cos theta r cos theta I plus beta and cos theta r minus beta. If you just multiply them, so just algebra, nothing more than that. 1 plus beta cos theta I into cos of theta r minus beta equal to 1 minus beta cos theta r into cos of theta I plus beta. Just simplify, multiply them. This is a cos of theta r minus beta plus beta cos of theta I cos of theta r minus of beta square cos of theta I is equal to, again multiply, cos theta I plus beta minus beta cos of theta I cos of theta r, and last term is beta square, right? Beta square and cos theta r, beta square cos theta r, cos theta r. If I take all the cos theta r terms in one side, this will give me cos of theta r. I am taking all the terms with cos theta r, theta r on one side. 1 plus twice beta cos theta I plus beta square. On the other side, we have 1 plus beta square cos of theta I plus 2 beta, twice beta, right? So this will give us cos of theta r. This will give us cos of theta r equal to 1 plus beta square cos theta I plus 2 beta, beta is v by c, divided by 1 plus 2 beta cos of theta I plus beta square, this term, right? You see now theta r is calculated, so theta r will be cos inverse of this quantity, right? And you see all the quantities on the right hand side, beta is given to you, right? The velocity of the mirror. Theta I is also supplied to you. Theta I, nu I, velocity, these are given to you. You have to calculate the quantities for the reflected one, angle for the reflected ray, frequency for the reflected ray, and so on. So as I told you earlier, we calculated nu r by nu I, right? For this equation, we got three different mu r by nu y. What was that? I'm just picking one of them. You can use any of them. 1 plus beta cos theta I. This we have already obtained, and 1 minus beta cos of theta r. Right now, you see cos theta is already obtained here. Right? You plug in cos theta here. So again, you have to just do one page of algebra. You just have to put this all the algebra. You just put this expression over here. Everything will come in terms of theta I. You see, theta r will be replaced by theta I. So you can put this cos theta r here. You put this cos theta r here and simplify it, and you will get. So I am not doing that. Just do it. 1 plus twice beta cos of theta I plus beta square divided by 1 minus beta square. So this is the solution of this problem. So now we have determined both the frequency of the reflected light nu r, because nu r will be this term into incident frequency. You see all the terms in the right hand side are the known quantities. Theta I is given to you, nu I is given to you, beta is given to you. So you have calculated the reflected frequency in terms of the inputted quantities. Also, you have calculated the angle of observation in the lab frame of for the reflected light in terms of the known quantities. So this was the problem. So by solving these problems, I just wanted to give you a flavor that what kind of problem I expect you to solve in the exam. You see, you can easily understand that this kind of problem can be formulated by anybody, right? You just have to consider, I mean, a given problem. See, here I am have given you a transformation for the along the x-axis. I can mix them up. I can give it for a separate direction. So things will change. Once you understand the underlying principle, you will be able to solve, right? So you have to practice these things. Okay, it is not necessary that I will give you only the problem that I am discussing in the class. Okay, because you have to learn these things. So that's my point, that you just understand what is the underlying concept, how to solve these problems, and then practice, right? And as I told you, there is no unique book there for such problems, right? That you just pick up a book and solve those problems, you learn everything. No, there is no such book. There are a couple of books, as I told you, for this particular topic which I am discussing right now, this relativistic electrodynamics. Jackson books, exercise 11 or 12 is a quite a good source of problems which you can consult. But of course, you will not find all the problems that I'm discussing. but again, these problems, as you can see, these are very simple problem, but you have to understand the underlying concept very clearly. So although I'm combining problems and theory both in my classes, because this semester is extended up to March, so we have still some time to discuss these things with detail. So that's why I'm trying this, but I am still not sure that how. I may not be able to discuss problems in each and every topics. Maybe I will give you one or two examples, and then you just have to practice similar problems yourself. Okay, so we have finished discussing about 4 wave vector. যদি কারো কোনো প্রশ্ন থাকে এখানে you can ask questions.
স্যার বলছিলাম
বলো।
আমাদের সেমিস্টার কি ফার্স্ট থার্ড দুটো সেমিস্টারই কি মার্চ পর্যন্ত
এটা দেখো আমার কাছে যেটুকু ইনফরমেশন, তোমাদের যে কোর্সটা আমি পড়াচ্ছি এখন ফার্স্ট সেমিস্টার তো ধরো তোমার শুরু হবে নভেম্বর থেকে, রাইট? তো ওরা অলরেডি আরো 1 মাস পিছিয়ে থাকবে তোমাদের থেকে। তো পরীক্ষাটা মোটামুটি একই সময় হয়, হয়তো 7 দিন 8 দিন 1 সপ্তাহ ম্যাক্সিমাম 10 দিন এরকম একটা ডিফারেন্স থাকতে পারে, রাইট? সেভাবে হয়তো এক্সাম শিডিউলটা তৈরি হয়। যেহেতু ওদের একটু দেরিতে শুরু হচ্ছে, ওদেরকে হয়তো 1 সপ্তাহ 2 সপ্তাহ ম্যাক্সিমাম বেশি সময় দেওয়া হতে পারে। মোটামুটি একই সময়ই হবে, ধরে রাখো 1 সপ্তাহ মতো এই হবে আর কি। তো সেই হচ্ছে তোমরা একটু সময় বেশি পাচ্ছ ওদের থেকে, ফার্স্ট সেমিস্টার থেকে। আচ্ছা, আরেকটা জিনিস আজকে আসলে আমার ক্লাস, একটা জিনিস তোমাদেরকে আমি যেহেতু আগে থেকে নোটিফাই করিনি, আমার বাবা আসলে খুব ক্রিটিক্যালি হসপিটালে ভর্তি আছেন। তো যেহেতু তোমাকে বলিনি আমি, তাই লাস্ট মোমেন্টে ক্লাসটা ক্যান্সেল করলাম না। আমি কালকে ক্লাসটা নিতে পারবো না, হ্যাঁ। একেবারে লাস্ট মোমেন্টে আমি আসলে ঘন্টাখানেক আগে থেকে ইনফরমেশন পেয়েছি। আমি ভাবলাম লাস্ট মোমেন্ট আমি যেহেতু এখানেই শান্তিনিকেতনে রয়েছি, তাই ক্লাসটা নিয়ে নিলাম। আমি আগামীকাল ক্লাসটা নিচ্ছি না, ঠিক আছে? আর তোমাদের পুজো ভ্যাকেশন যা নোটিশ এসেছে আমাদের একাডেমিক হিসেবে, একাডেমিক স্টাফদের জন্য, তাতে আগে ওটা 10ম পর্যন্ত ছিল, সেটা এক্সটেন্ডেড হয়েছে 29th 31ও ছুটি মনে হয় শনিবার বলেছে। সুতরাং নভেম্বরে ক্লাস হবে এরপরে, নেক্সট ক্লাস, হ্যাঁ। সুতরাং নভেম্বর মাসে যেদিন আমার ক্লাস আছে, সে ফার্স্ট হোক সেকেন্ড হোক থার্ড হোক, তুমি দেখে নিও, সেদিনই ক্লাস হবে আমার, ঠিক আছে? আর যেগুলো আলোচনা করেছি আমি, হ্যাঁ, এর মাঝে ঠিক আছে, তোমরা যেগুলো পড়েছি এগুলো তোমাদের কিছু দেখে রেখো। জাস্ট আমি এখনো 4 ভেক্টরটা কন্টিনিউ করবো কিছুটা প্রবলেমস যেগুলো বললাম, যে আমি যে প্রবলেমগুলো আলোচনা করছি ক্লাসে, যদি তোমরা এগুলোই ভালো করে ফলো করো, তোমরা মোটামুটি আমার মনে হয় যে সিমিলার টাইপের প্রবলেম করতে পারবে, রাইট? আমি মারাকাটারি কোনো ডিফিকাল্ট প্রবলেম পরীক্ষা তো দিই না, আশা করি একটা কোর্সে যারা শিখতে পারবে। আমি চাইবো শুধু তোমরা বেসিকটা ভালো করে শেখো, রাইট? আমি এটাই চাইবো যে একটা কোর্স করলে এখানে তোমরা যেন বেসিকটা ভালো করে শিখতে পারো। তারপরে দেখো, নিজে শেখার তো কোনো শেষ নেই, তুমি সারা জীবনে শিখবে, রাইট? আমিও শিখছি, সবাই শেখে। এখন তো ইটস আপ টু ইউ, কতটা তুমি এফোর্ট দেবে, কি শিখতে চাও। কোর্সে যতটা আমি এক্সপেক্ট করি সেটা হচ্ছে যা ক্লাসে পড়াচ্ছি, ইউ হ্যাভ টু আন্ডারস্ট্যান্ড দ্য কনসেপ্ট, রাইট? কোনো ডাউট থাকে, ইউ আর অলওয়েজ ওয়েলকাম, ইউ ক্যান ক্লারিফাই ইউর ডাউটস, রাইট? এর বাইরে আমি আর কি বলছি না। তুমি এক্সট্রা প্রবলেম যা বলেছি, যে বইগুলো রেফার করেছি আমি, মোটামুটি এই বইগুলো আমি কনসাল্ট করি, রাইট? বাদ বাকিটা তুমি এবার মোটামুটি আমি নিজে যেটা সিনথেসাইজ করে আমার নিজের মতো করে পড়াই, সেটা এবার তুমি কোনো একটা ইউনিক বই আমি রেফার করতে পারবো না, যেখানে তুমি গেলেই তুমি সব প্রবলেম যা পড়াচ্ছি পেয়ে যাবে, এখন নেই কোনো বই। সুতরাং আননেসেসারিলি ডিলিট করে লাভ নেই, রাইট? তো আমি যা বললাম, যে এই জ্যাকসন, গ্রিফিথ, ওই যেটা বলেছি হেলিডেরিজনিক, আর তোমার ল্যান্ডাউ লিপসিচ, এই 4টা বই আমার মনে হয়, আমার পার্সোনাল যেটা মনে হয়, এগেন দেয়ার আর মেনি বুকস আউটসাইড। তো এই বইগুলো মোটামুটি বেসিকটার জন্য, ল্যান্ডাউ লিপসিচ যেটা আমি বারবার বলি না রিপিটেডলি, কারণে ল্যান্ডাউ লিপসিচ ইজ ওয়ান অফ দ্য বেস্ট বুক ইন দিস ফিল্ড, কিন্তু ওটা তো সবই সিজিএস ইউনিটে রয়েছে। তো যেটা অনেক সময় কনফিউশন হয়, ইউনিট কনভার্সন করতে হবে, ফর্মুলাগুলো পাল্টে যায়, কিন্তু কনসেপ্টগুলো তুমি ওখান থেকে পড়তেই পারো, রাইট? কনসেপ্টগুলো জিনিসগুলো পড়তেই পারো ওখান থেকে। ঠিক আছে, ওকে, অলরাইট। পুজোর পরে দেখা হবে, সবাই ভালো করে পুজো কাটাও। ঠিক আছে,
থ্যাংক ইউ স্যার।